Greetings and a very hearty welcome to this course. Quantum mechanics and symmetry of the hydrogen atom is the topic of our discussion for the first unit, and what we will do in this is to address this question which perhaps some of you are at least familiar with. Have a look at the elements in the first group of the periodic table. Okay, hydrogen, lithium, sodium, potassium, rubidium, you are all familiar with this. These are all first group elements, and they are all in the first group because there is something common about them. What is common about them is the electronic configuration. All of them have got one electron in the outermost shell. For the hydrogen atom there is nothing like an outer and an inner because there is only one shell, and each atom in the first group of the periodic table has got this ns1 configuration in the ground state. Of course, this electron can be excited to different states, that is a different matter, but in the ground state the configuration is 1s1 ns1. And all of you have done some experiments in the optics lab and worked with the sodium vapor lamp. So you are familiar with the D1 D2 lines of sodium, right? These are the 5890 and 5896 angstrom wavelength yellow lines of the sodium vapor lamp, and as I am sure you are familiar from your first course in quantum mechanics, these transitions are from the 3p level of the sodium to the 3s. Now all of you are aware of this, and it is obvious if these energy levels were degenerate, and you know what degeneracy means. If you have linearly independent functions which belong to the same eigenvalue, then you have degeneracy, right. So if 3p and 3s wave functions were to be degenerate, if they were to have the same energy, then 3p which is here and 3s which is here, there is a transition from 3p to 3s, but if they were degenerate they would be at the same level, and there could be no transition from 3p to 3s, and there would be no emission of light, and there would be no absorption as you find in Fraunhofer lines. Okay. So it is obvious that the energy of 3p is different from that of 3s in the sodium atom, but in the same group if you go to the hydrogen atom, which is the simplest of all of these atoms in the first group, the energy of 3p and 3s for the hydrogen atom is exactly the same. Okay. The energy eigenvalues of the hydrogen atom, they go as 1 over n square, they do not depend on the L quantum number. So the question that one would ask is this, that the energy of 3p is different from that of 3s for the sodium atom, but it is not the case for the hydrogen atom. Yeah, and this obviously has got serious implications in spectroscopy, as is obvious to you. So the question here is, why the spectra vary? As you can see, this slide was made when that why this Kolaveri song was, it had gone viral, but I think most of the people have happily and fortunately forgotten that song now. But we do have this worry as to why is the spectrum of the hydrogen atom, which is really simple, this is the simplest atom that you can think of, and this is the question that we are going to address in the first unit. Okay, we are going to study the quantum mechanics of the hydrogen atom, and we will try to get an answer to this. Now whether it is 3s, 3p and so on, essentially we are talking about discrete energy levels, and we often say that quantization means having discrete energies. Do we all agree with that? Now is having discrete energy levels the signature of quantum mechanics? It is not. What is the signature of quantum mechanics? Do you understand this question as to what is the signature of quantum mechanics? Because here we are dealing with a discrete spectrum, and we have to ask this question as to what is the signature of quantum mechanics. Is this always the case, and just what is the signature of quantum mechanics and what is really meant by quantization. So, very often it is suggested that quantization means having discrete energy levels. Anybody has a comment or a question on this? You agree with this or you do not agree with this? What is quantization? I need you to start talking. Will anybody like to suggest a comment on this?
Only particular values of some property is allowed. So that is quantization.
That is quantization. Anything, any other answer?
Eigenvalue.
What is quantization?
So the Planck's constant must appear in some formula.
That's one way of looking at it. What else? Any other? Yeah, let me take this answer and then come here. Somebody here.
Quantization results when we impose the condition that the wave function should be bounded.
Any other?
Physical properties are given in terms of operators. So your operator can change the state, and only when the state matches, you have a particular eigenstate. So that's where discrete energy levels come.
What's your name?
Pranay.
Pranay. Okay. We will get the correct answer. Yours came pretty close but not exact, and all the other answers had something lacking, and you will see what was missing in these answers. So it is important to us that we discuss quantum mechanics, because quantum mechanics and atomic physics have developed hand in hand, and what we are going to study, this course is about atomic physics primarily, but quantum mechanics will be developed along with it. And I would like to quote Feynman here, who says in his volume 1 section 1-2 that if in some cataclysm, which is a catastrophe, I had to consult a dictionary, I did not know it, if in some cataclysm all of scientific knowledge were to be destroyed and only one sentence were to be passed down to the next generation of creatures, what statement would contain the most information in the fewest words? This is the question which Feynman raised, and he goes on to answer it saying that I believe it is the atomic hypothesis that all things are made of atoms. So obviously it is extremely important to learn atomic physics in a very thorough and rigorous manner. So this is a very exciting subject. If you just see the kind of Nobel Prizes which go to this field, it averages to almost 2 per decade in the last 3 decades, and most of you would be familiar with some of these big names who have done seminal work in atomic physics. And of course there have been many contributors right from Dalton or even prior to Dalton perhaps, and a large number of scientists have contributed to this field. So we will touch upon the contributions of some of them as the course develops. Now I had a review talk some time back which is on the YouTube, and it would give you an overall survey of atomic physics, and you will find the link to this from my web page. But this is about a 2-hour talk which is about, it reviews the developments in atomic physics, and what we have set out to do now is a full lecture course on atomic physics. So we begin with the simplest of all the atoms, the hydrogen atom. 1 electron, 1 proton. This is the simplest thing that you can think of. It is a 2-body system, and essentially we will discuss the symmetry and quantum mechanics of the hydrogen atom in the first unit. Now this course is meant for those of you who have some exposure to quantum mechanics, not necessarily a whole lot, which is why we are doing the hydrogen atom again, but some exposure to quantum mechanics is certainly assumed. We will learn about the complete set of good quantum numbers for the hydrogen atom. We will discuss what is meant by a good quantum number, what are the associated symmetries, constants of motion, all of these things we will discuss in this unit, and in particular we will discuss what is known as the SO4 symmetry of the hydrogen atom, and how the properties of the SO4 symmetry lead to the eigenspectrum of the hydrogen atom, which is different from that of the sodium atom with regard to the question that we raised. Okay. So, that answer finally comes from an understanding of the SO4 symmetry of the hydrogen atom. So, that is what this unit is going to address. So, it will help us understand the difference between the eigenspectrum of the hydrogen atom with that of the other elements in the first group of the periodic table. So, let us begin with this spectrum of the hydrogen atom. These are 4 lines of the hydrogen atom, very precise measurements done by Angstrom in 1853. He develops one of the first spectrometers. So, the wavelength unit is named after Angstrom. Do you see any pattern in these numbers? You have these numbers 4101.2, 4340.1, 4860.74. Okay, there is a certain, there are 4 numbers in front of you, and if you were to be given some 4 numbers like 3, 6, 9, 12, you would immediately tell me what the pattern is. And when you look at a set of numbers like this, do you recognize any patterns? Does it offer some clue? Do the numbers suggest some pattern? If you knew it, maybe you do. If you did not know it, it is not something which is very easy to discover. Would you agree? It is not easy to discover that pattern. Now, Bohr at his age of 60, which is good news for me, in 1884 he actually found the pattern in these numbers, and this is the pattern, that all of these 4 lines have got wavelengths which fit exactly the formula which you have on the screen. The lambda must be b into n square by n square minus 4, with n going from 3, 4, 5, 6 for these 4 lines, but also the proportionality b is again not a very simple number to come up with. It has got a very peculiar value, which is 3645.6 angstrom, and Bohr figured this out. And as a matter of fact, I am sure all of you know this formula. You probably studied it in your high school and then in your college, right? Despite that, it did not occur to you that maybe I already know the pattern, and this is a pattern which Bohr discovered. I think it is, to me, it is very impressive insight in arithmetic that Bohr could figure this out. Not only that, Bohr was of course able to do it because he was a teacher in a girls' school and he was teaching mathematics. So, maybe girls have very sharp arithmetic skills, and that might have pushed Bohr's skills. But Bohr also predicted that there would be other lines in the infrared corresponding to n equal to 7, 8, 9, etc. Now, these lines were not seen at that time. Okay, there were no detectors in that spectral region, but he predicted that there would be these lines. He also predicted that the number 4 that you see in the denominator, n square minus 4, could be replaced by the square of 3 and 4 and 5, and then you would get other spectral lines, and all of these lines do exist. So, Bohr not only found the formula, but he also predicted, and these predictions turned out to be correct. So, this is really amazing. Rydberg also discovered that these lines correspond to a certain formula, which is the Rydberg formula, which in fact is the same as Bohr's formula, except that this is for the reciprocal wavelength, and Rydberg got this formula quite independent of Rydberg, quite independent of Bohr, although it came 6 years later, but great minds often think alike, and Rydberg discovered this relationship quite independently and on his own. Now, this is a semi-empirical formula, and you know what is meant by a semi-empirical formula. Semi-empirical means that okay, you have got some experimental observations, you do not really have a theoretical model, but you do some mathematical jugglery and you figure out that okay, all of these numbers fit this particular formula. So, this is semi-empirical, it is not fundamental, it is not theoretical as such. Then later, I mean that was toward the end of the 19th century, and then in the beginning of the 20th century, Niels Bohr came with what we call as the Bohr's model of the hydrogen atom, and this model, which I am sure all of you have studied, also gives you the 1 over n square term. And this model is based on this idea that okay, you have got a central nucleus and then electrons revolve it around this nucleus in orbits, but the electrons do not radiate during this acceleration, and with a set of postulates that we call as Bohr's postulates, quantization of angular momentum and everything, you are able to get the 1 over n square formula, right. So, all of you have studied that. Now, this is certainly based on a set of postulates, so it is not exactly semi-empirical, it is postulatory, and it worked. The orbits that Bohr invoked are like Kepler orbits. So, there is a very close parallel between the Kepler model of the planetary motion around the sun, and the Bohr Sommerfeld model of the hydrogen atom. So, this brings us back to the central problem in mechanics, and it is the same whether we are dealing with classical mechanics or quantum mechanics. Okay, the central problem in mechanics is how do you characterize the state of a mechanical system, and how does this system evolve with time. This is the fundamental question. Now, in classical mechanics, you pose the mechanical problem, solve it, and the solution appears as a trajectory, okay, the locus of the movement of the particle. That is the solution to your mechanical problem, and that tells you how the state of the system evolves with time, because a locus of the particle or the trajectory of the particle is a time path of the particle in the phase space. Okay. So, that is the solution in classical mechanics, of course subject to appropriate initial conditions. Now, this comes from our understanding of classical mechanics, and of course the foundations were laid by Galileo, who discovered the law of inertia. What we call as Newton's law of inertia was actually discovered prior to Newton by Galileo. The credit goes to Newton because he integrated this into his scheme of dynamics, but Galileo was able to discover the law of inertia, and then Newton figured out that okay, what is it that is needed to disturb equilibrium of a system, and he invented the idea of a force. That force is the agency which disturbs equilibrium, and that is the second law, F equal to ma, right. The disturbance from equilibrium manifests itself as acceleration of the object. This is what Newton formulated in his scheme of mechanics, and this is really the heart of the principle of causality and the linear response theory in Newtonian dynamics. Now, alternative formulation of classical mechanics exists in the form of Lagrangian or Hamiltonian, and this is based on the principle of extremum action, that action is an extremum, any variation and that would vanish, and the condition that must be satisfied such that action is an extremum, that condition is what gives you the equation of motion. Okay, that is the Lagrange's equation. You can also get Hamilton's equations correspondingly. Now, in these schemes, in classical mechanics, the central idea is the following, that the state of the system is described by position and velocity q and q dot, or alternatively by position and momentum q and p. Okay, this is the heart of classical mechanics, and then its evolution is described by how this state evolves with time. So, dynamical variables are functions of the state of the system, position and velocity or position and momentum. So, you can describe the system either by q and q dot, or equivalently by a function of q and q dot, which is the Lagrangian, or a function of position and momentum, which is the Hamiltonian. And observables are then various functions of these independent variables which characterize the state of the system. Now, this is how classical mechanics works. Now, the question is, what would happen if you measure position and momentum? You carry out a measurement of position, record your answer, store it, then you carry out a measurement of the momentum, record that answer, you are happy, you can go ahead. But if you decide to repeat your measurement on the position, okay, it would not be guaranteed that you will get the first answer that you got at the first measurement, you would get a spread, right. So, you cannot get same answer to repeated measurements of position if you intervene these measurements by measurements of momentum. Okay. This is the principle of uncertainty, and the reason you cannot get consistently the same answers to position and momentum measurements is not because of the principle of uncertainty, it is the other way around. It is because you cannot get same answers consistently that the uncertainty principle exists. Okay. So, do not put the cart before the wheel. Okay. So, now we have a problem that if repeated measurements of position and momentum do not give you the same answer, if a measurement of momentum is intervened by a measurement of position and vice versa, you do not get the same answer, then it would be impossible to characterize the state of a system by position and momentum. Our contention in classical mechanics is that a state of a system is characterized by position and momentum, and you cannot do it because repeated measurements do not give you same answers. So, you cannot do it. You cannot describe the state of a system by position and momentum or by position and velocity, and if you cannot do it, then how do you do mechanics? Because the central problem in mechanics is how do you characterize the state of a system and how does the system evolve with time. And if you had agreed to characterize the state of a system by position and momentum, you cannot do it anymore. So, you have to find a different mechanism to do it, and that is quantization. Okay. You have to abandon this approach that the state of a system is described by q and p is something that you cannot carry on any further because it does not take you anywhere. So, you have to find a new theory, and this new theory is quantum mechanics. Whatever you do to get into this theory is quantization. It is not just having energy spectrum which is discrete. That energy spectrum is discrete is one of the consequences of quantization, but it is not the signature of quantum mechanics. Okay. You have to do something else, and if you cannot describe the state of a system by position and momentum, then you cannot set up Newton's equations, you cannot set up Lagrange's or Hamilton's equations, you cannot get solutions as trajectories and locus, right, and then trajectories do not exist in quantum mechanics. So, what is a Bohr-Sommerfeld orbit? It does not exist in quantum mechanics. So, the Bohr-Sommerfeld model of the hydrogen atom is again, certainly it gives you the 1 over n square formula, it explains the spectrum of the hydrogen atom, but it is really not quite quantum mechanics, although it is quantum mechanics to a certain extent, because one of the postulates of Bohr made use of the Planck's constant, as one of our friends suggested, that it has to have the Planck's constant, and action is quantized in the Bohr model. So, these things are there, but it is not really quantum mechanics. It is what we now call as old quantum theory. It is not formal quantum theory as such. There can be no orbits in quantum mechanics. So, any model of the hydrogen atom which is based on orbits really is not tangible. So, quantization cannot follow the path of Niels Bohr, and Banish-Hoffman called it by saying that the atom of Niels Bohr Niels. Okay, it does not work. Okay, so, in her book Strange Story of the Quantum, she has got a chapter whose title is The Atom of Niels Bohr. The next chapter is The Atom of Bohr Niels. It does not work, it cannot. So, this model is wrong. All this picture of orbits is not correct. So, you have to abandon the classical description completely. You need to get into quantization, and now we can really answer what quantization is. And quantization suggests that you do not describe the state of a system by Q and P anymore, but you describe it by a state vector. Dynamical variables you represent by operators, and this is something which Pranay suggested. And then these look like some abstract quantities, but then as Dirac tells us in his book Principles of Quantum Mechanics, which I strongly recommend, you begin with this, and as you develop the algebra further, gain more experience with it, you are then able to figure out how to connect these things to observables. Okay. State vectors by themselves are mathematical creatures which exist in the Hilbert space. These are vectors in a mathematical space which were named by John von Neumann after his guru David Hilbert. So, these are the Hilbert state vectors, and then these operators operate on these state vectors, and then you need to develop the algebra further. The moment you do that, you have quantized the system. This is quantization, that you dispense with classical description in terms of position and momentum, replace these Q and P, which are dynamical variables in classical mechanics, by operators, the position operator and the momentum operator. You have quantized the system. We have not talked about discrete energy spectrum or anything like that. Okay, that is not the signature of quantum mechanics. This is the signature of quantum mechanics. So, you have a state vector, but you are going to label this state vector in some manner. You need to find a mechanism to designate the state vector. So, the next question is, how do you label these state vectors? So, what you are going to do is to figure out a mechanism to label these state vectors. So, let us discuss that very briefly. If you have an operator which operates on a state vector, you get a new vector. You have not put labels anywhere. However, if the new vector is proportional to the old vector, you just have a proportionality between the two, then you have an eigenvalue equation. Okay? Then you pick the eigenvalue and use that eigenvalue to label the vector. So, insert this eigenvalue into the vector. This is how you label the state vector. Okay? See how we have written the eigenvalue equation. We had an operator operating on a vector, and then when this I do not know what is happening over here. Okay. So, you get a proportionality, you recognize this proportionality, put this into the vector as its label, and then you have a complete eigenvalue equation. So, we have not written this eigenvalue equation from left to right. Okay. We let it operate, got a new proportional vector, then picked the proportionality and inserted that into the vector. So, we have hopped a little bit, okay, the way you play the knight on a board of chess, and then you have the complete equation, right. So, it does not go completely from left to right. So, this is how you write the eigenvalue equation, and this is what measurement does to a system, that when you perform a measurement on a system, the system collapses into an eigenstate, and this is the eigenvalue that you use to describe the state of the system. Now, fair enough, this is the approach which was developed of course by Schrödinger and Heisenberg, as you have learned in your course in quantum mechanics. This is a probabilistic theory, it has got statistical elements, and Heisenberg, Bohr, many others contributed to it. And statistics and the probabilistic elements in quantum mechanics is something that one of the persons who was the originator of quantum mechanics was not comfortable with, and that was Einstein. Einstein contributed to quantum mechanics. In a certain sense, quantum mechanics has its beginnings not quite in the work of Max Planck, because Max Planck did it just to fit the black body radiation formula, he never agreed with it himself. But only when Einstein explained the photoelectric effect using that hypothesis did people actually grasp the meaning of energy quantization. So, Einstein actually contributed to the development of quantum mechanics, but he was not happy with the probabilistic version, and he was very troubled by statistics, by probabilistic things, and he felt that okay, all this probabilistic things and so on do not fit into his mind, in his imagination of how God would have created the universe. So, he went on to say that God does not play dice, and there are these famous 1927 debates between Einstein and Bohr, which Bohr always won hands down, and he found fallacy in Einstein's arguments and convinced him that yes, probabilistic nature is intrinsic to quantum mechanics and there is nothing wrong about it. So, he went on to tell Einstein that it is not your business to tell God what to do. So, quantum theory does have a probabilistic element, and it really came to stay in the at the Solvay conference in the debates of Einstein and Bohr, and we will designate it by a label which will come from the eigenvalue of the measurement. Okay. And there can be not just one eigenvalue, there can be more operators for which you can have an eigenvalue equation satisfied, because you want to get as much information about the system as you possibly can. So, what you will like to do is find out the operator corresponding to a measurement, carry out that measurement, which is the same thing as operating on the state vector by the operator. So, you have to have a one-to connection in your mind between the experiment which is being done and the corresponding quantum mechanical simulation. Okay. So, do not separate experiment and theory in your mind, it is exactly that. Okay. They are completely synonymous in this description. The system collapses into an eigenstate, okay. But then you ask what else can be measured, and if you can find everything else that can be measured, but not all measurements are compatible, some of them are and some of them are not. We already know that position and momentum are not compatible, which also mean that potential energy and kinetic energy will not be compatible, right. But some measurements will be compatible, and you stack as many measurements as possible so that you get the complete set of compatible observables or complete set of commuting operators, and this is Dirac's vocabulary, which is very nice because the CSCO stands for the complete set of compatible observables as well as complete set of commuting operators. and you can then find another measurement B. You carry out this measurement, the system will now collapse into an eigenstate of B, but it remains in the eigenstate of A, because A and B are compatible in this case. So, if you go back and repeat the measurement of A, you will recover the earlier value which was A, which was the lowercase a. Okay. So, you now stack all the compatible measurements and then you get a complete set of commuting operators which commute with each other, so that their commutator vanishes. Okay. And then there are simple theorems that they can be simultaneously diagonalized, etc., and some of these things you have learned in QM1. So, this is quantization, and we have to ask what are the considerations which govern the choice of operators, and you would have studied again in your first course in quantum mechanics. So, I will not spend any time discussing this, but I will quickly remind you that you represent the position operator by Q operator, which is Q times the unit operator, and the momentum by the gradient operator, which is the minus IH cross gradient operator. So, this is an appropriate operator for momentum, and the reason this is so, because momentum is the generator of translational displacement in homogeneous space. And this is the fundamental reason that momentum is represented by the gradient operator, because when you find out what is the displacement operator, you get these forms of the momentum operator. It is not just a postulate that P is minus IH cross gradient, it comes very naturally from the fact that momentum is the generator for displacement in homogeneous space. For the hydrogen atom, you have got radial symmetry. Okay. So, you will look for the generator for rotations in isotropic space. So, that will lead you to the angular momentum. So, for the hydrogen atom, this would be an important operator. What you get, as you find in Sakurai's book Modern Quantum Mechanics, is that you get two alternate and equivalent expressions for the operator for infinitesimal displacement, translational displacement, and if these two are to be equivalent, then you must have the momentum to be described by minus IH cross gradient, right. So, you carry out a similar analysis for the angular momentum and you will get the corresponding operator for angular momentum. So, you have displacement, translational displacement in homogeneous space for the linear momentum operator, and in isotropic space where you carry out infinitesimal rotations, find out what is the generator for this and you will get the operator for the angular momentum. This comes from the rotational symmetry of the hydrogen atom, which is the 1/r potential. So, consider these rotations. This diagram is self explanatory. You have got the rotated vector with r subscript capital R, which is the original vector r plus this infinitesimal tiny displacement delta r, which is nothing but the cross product of delta phi and r, right. Delta phi is an infinitesimal rotation vector. Finite rotations are not vectors, but infinitesimal rotations are. Or you can write this as a determinant for simplicity and write the new vector as a column vector and express this result of a rotation by a matrix transformation. Okay. So, when you do that, you get the matrix for the rotation operator, and I will carry on from this point in the next class. If there are any questions for now, I will be happy to take.
So, in the previous slide, not just previous, before that, that B operator acting on. So, here actually we are doing the experiments, measurements we are doing for one particular property, right. At a time when you are doing a measurement, you are doing either A or B. Yeah. So, once we do the measurement A on a ensemble or whatever, the system is collapsed to one particular state.
Correct.
So I mean, if you are doing that again on that system, I mean, it's already it is in this particular, I mean,
Eigenstate.
yeah, but the I mean, can we do again that B on that particular system?
What's your name?
Pranav.
Your Pranav.
Yes.
See, your question goes down to the very heart of quantum mechanics. Because what is really happening is you perform a measurement, the system collapses into an eigenstate of that measurement. Now you perform some other measurement, which is a measurement of B. Okay? Now when you perform a measurement of B, the system will collapse into an eigenstate of B. Now if you repeat measurement of B, you will always get the same answer, no matter how many times you carry out, because the system remains in an eigenstate no matter how many measurements are repeated. So it remains in an eigenstate of B. So let us say you perform 13 measurements of B, and now you come back and make a measurement of A. Now you will get the same answer as you had got earlier if and only if A and B are compatible, not otherwise. If A and B are compatible, measurement of A will recover the original value, the eigenvalue of the measurement of A, and the system will then remain in eigenstate of A, but it will continue to remain in the eigenstate of B, because it is a simultaneous eigenstate of both A and B. Okay, which is what you really mean when you say that operators which commute have got simultaneous eigenstates. I am sure you have done that theorem. And then you perform measurements of A, you can perform another 17 measurements of A, and then come back up and carry out a measurement of B, you will recover the original value. But this will not happen if A and B are not compatible measurements and the corresponding operators do not commute. That is exactly what happens to position and momentum. Is it clear? Any other question? But this is quantum mechanics, this is really the uncertainty principle. Any other question?
Is it like repeated measurement of an observable is not allowing my system to evolve?
Well, the system continues to evolve, but the evolution, the temporal evolution can be only by a phase factor. Okay, so it is not that it stagnates, there is a time evolution, but the time evolution of the stationary state will be only by the phase factor, which is the e to the minus I omega t, or e over h cross t. Okay. But if it is not an eigenstate of that measurement, what will happen is that the operator will throw the system into a different state, and the new state will then be a linear combination of the original eigenbases. So it will not be in a pure state anymore, it will be in a mixed state. Okay, it will be in a state of superposition. Is that clear? Any other question? Complete set of commuting observables correspond to a complete set of experiments which can be carried out, different experiments. Okay, because you cannot have any additional measurement. Whatever can be known about the system, yeah, it has to be compatible, but whatever can be known about the system, like we want to know something about our friend over here, and we want to know everything about him. What is his name, what is his address, who his girlfriend is, everything. Okay, once you get all the information, you are done with it. You cannot get any further information about it. When you catalog all of this information together, you have a complete set of observables, and that is what a physicist likes to do to an object, because given the hydrogen atom or given any quantum system, okay, any physical system, all physical systems are quantum systems, but given any physical system you like to get information about the physical system and you like to get as much information about it as possible. That is the reason you do not stop at one measurement, you carry out the next measurement, and the interesting thing is that it is not guaranteed that after the performing the next measurement you come back and repeat the first measurement you will get the same answer. That is the reason you have to look for compatible measurements, and once you have exhausted everything that can be measured you get a complete set of compatible observables and correspondingly complete set of commuting operators, CSCO. Okay, so I guess we will stop here. I will be happy to take questions by emails also.